Good morning, all of you. Today we shall discuss about the topics of Unit 5. So the title is Press Working. Press Working. So we should understand that press working is a chipless manufacturing process. That means no chips or least amount of chips may be formed. And further, it's a sheet metal working process. So it is nothing but a sort of sheet metal process, right? Further, this sheet metal is process is carried out using a press. It is this press working process is different from sheet metal working of a workshop. The chief or main difference is we are going to carry out this sheet metal working using a machine which we call it as press. So press working operations, if we try to look at, they produce a variety of components: metal desks, file cabinets, bodies of different appliances, LPG gas cylinders, keys, household utensils, jewelry, aircraft fuselage, automobile components, washers, bushes, retainers or cages for the ball bearings, bathtubs, wheel rims, fan blades, watch watch gears, etc., etc. So many components, so many different type of components. Wherever sheet metal is involved, we can make them using the press working process. What are the different press working operations? So we can categorize the press working operations into two types. The first one we call it as die cutting operations. Die cutting operations. The second one, forming operations. So the basic difference between these two, it is the die cutting operations. Cutting action is the main activity or the main operation. So here, to cut the sheet metal along a particular profile or contour, the workpiece is to be stressed beyond its ultimate strength. So we have to reach this ultimate value. In case of die cutting operations. On other hand, when we talk about the forming operations, we never go up to ultimate strength. So our operations may cross the yield strength or has to cross this yield stress or yield strength, but we never go till ultimate strength. So that is the main difference. Let us look to the different die cutting operations. Before going to the different die cutting operations, let us have the names of the forming operations. Some of the forming operations are bending, deep drawing or cup drawing, embossing, coining, bulging. Likewise, spinning. Spinning also can come into the category of the forming operations. Whether it's hot spinning or cold spinning. So spinning also comes into the category of this forming operation. Okay, now let us look at the die cutting operations. So there are different die cutting operations. The primary or the first operation of importance, it is blanking operation. So blanking operation is the operation where a flat shape from the sheet metal is produced. So this article punched out, we call it as blank or slug. Blank or slug. The hole and the metal left over behind is discarded as waste. So we also call sometimes this waste as scrap. It is usually the first operation in a series of operations to produce a complex component. Right? You can look to the diagram, right? The basic diagram. So to the left side, the material which is coming inside, which is being pushed inside. So that we call it as stock. The material or the product which falls down, that we call it as blank. Other name is slug. To the left side, what is coming out, we call it as scrap or skeleton. Piercing operation. This is a cutting operation where holes are produced in sheet metal. Punching is similar to blanking, except that in punching, hole is the skeleton, except that hole with its skeleton is the desired product, and material punched out is the waste. So you can look to the difference. So in case of piercing, the hole that has the material that has been punched out, it is the scrap, and the material which is remaining, it is our product. On the other hand, when we take the blanking operation, so what is punched out is the product, and what remains is the scrap. Next, notching. This is the operation where metal pieces are cut from the edges of the sheet metal. This operation is necessary to carry out further operations like bending. So on the edge, we may cut off some portion, right? So we call them as notches, and the operation is called as notching. Next, perforating. Perforating is the process where multiple holes are produced. Multiple holes, of course, small sized holes, they are produced. So that is known as perforating. The process can be used for producing sieves. So in addition, this can be used for producing body of electronic appliances, chairs, right? So the perforations are made. So perforations made for good or easy circulation is made for good or easy circulation, right? Next, trimming. So this is an operation where excess material is removed from the periphery of a formed component. So it is an operation which is performed on a formed component. On the formed component, what you are going to do is you are going to remove excess material, excess unwanted material. So this is an excess unwanted material. For example, I want to, if I look to a cup, it has a rim which is uneven due to misstrike. Misstrike means the punch is not going to hit exactly at the center of the disc. Instead, it is offset. So in that situation, you are going to have a rim which is ununiform. So such a type of rim has to be removed. So that is this operation where we remove this, we call it as trimming. Next is shaving. The edges of a blanked part, they are often rough, uneven and unsquare. So rough, uneven, unsquare, right? So accurate dimensions geometry when we require, we have to remove a thin strip or slice of the metal along the edges. So along the edges, we have to remove this material. So that operation is called as shaving. It has to understood that a very small clearance, a very little clearance between the punch and die is to be maintained, because this is a precision operation where we obtain smooth edges, square edges and irregular edges. Next, slitting. Slitting is the operation of producing thin slots throughout the workpiece. Lancing. It's an operation in which the punch cuts on 3 or 4 sides, or at least 2 or 3 sides of the profile, and bends about the 4th side. Thus, it is a combined bending and cutting operation. Right? You can see. So the punch moves down, it cuts on the three sides, and on the fourth side, it is going to produce a sort of bending, right? So this is a bent portion. So that is known as lancing. Next, nibbling. So nibbling, it is an operation where you are going to move a small punch. So this punch, we call it as nibbler, small punch. So it continuously moves up and down. Now the sheet is fed through the gap, and many overlapping holes are produced in this manner. So you are going to produce many overlapping holes. So nibbler moves along this path, and it makes multiple holes, and you can find these holes are all overlapping holes. So on account of this, it is possible to punch a contour by using a nibbler where the shape is complex. So complex contour is produced, right? So this is the operation which we call it as nibbling. Next we have operations cutting off. This cutting off an operation is an operation where uh, the separation of material takes place along a single line. So this is called as single line cutting. So cut along a single line. So single line cut. The single line cut is called as cutting off. On the other hand, we may have a double line cutting. So cut along two places. So that is called as parting off, right? So you can find. So this is a sort of double line cutting, right? So this cutting off, parting off operations are required in the last stages of cutting. When we talk about the materials suitable for press working, we generally go for soft materials, the materials which are not too hard. So of course, here also we should differentiate. Many times we take the materials which are suitable for press working based upon whether it is a die cutting operation or forming operation. Generally low carbon steels, non-ferrous metals like aluminum and its alloys like aluminum, further aluminum, titanium, zinc, etc. So such type of materials are more preferred for press working. So starting material is in the form of sheet or strip thickness from 1/10 of an mm to 8 mm. During this press working, the sheet wall thickness is generally constant and varies only by a small amount. The metal must be free from scales before sheet metal working. The scale can be removed by pickling. So when we talk about the advantages of press working components, small weight of the components, very high rate of production possible, as much as some 5,000 number of components per hour, lesser labor requirement, higher utilization of machine, and finally, low production cost. Next, good size and shape accuracy, which does not generally require any further machining. Lastly, uniformity of components. Next, press working components, the equipment. See, when we talk about the principal machine which is used in this press working, we call it as press, right? The requirement of a press is to supply a large amount of force on the press tools, that means tools attached to this press, for a short interval of time, which results in cutting by shear or deformation, that means purely plastic deformation of the work material. So the press should have facility to set up the forces, guide the forces in a controlled manner, right? So there are different issues related to press, such as source of power, number of slides, type of frame. So here you can see a typical press, which we call it as OBI press, open back inclinable press, right? So this OBI press has so many parts. So you can find a flywheel which stores the energy. Um, that means, and it is actually connected to a motor. So from the motor, it receives the energy and it keeps on rotating. It stores the energy, and whenever the ram moves down, the energy will be supplied by this flywheel. You have ram to which the punch assembly is attached, punch die assembly is attached. And next we have a gap at the center. So the gap is provided to push away the component from front to back if it is necessary. Same way, we have the press more number of times as C type of press. We call it a C frame, it which permits us to feed the components from this side. So it is something like C shape. So into this C, from left to right or right to left, we can push the component as the work is over, so as to get the next component. So further, we can find this is the uh, RAM, and this is the die set. That means punch and die assembly. So we have this frame which is adjustable. Actually, it is called as open back inclinable press. That means its back is open. Further, it is inclinable. So we have a slotted screw arrangement. So this is slotted screw arrangement for tilting the machine. Next, we shall talk about a simple die set. So these are the parts of the die set. So we can find a punch and a die as the two main parts. So this punch and die block together, they act as cutting tools. So in addition to that, we have arrangement to move the punch down by the movement of the ram in a controlled manner. For that, we have guide bushings. So the punch holder moves around this guide post with the help of this guide bushing. And regarding the other parts, we have a die block fixed on the die holder or die shoe, below which we have a thick plate which we call it as bolster plate, and below it we have the machine bed. So we have stripper and many other parts. This is only a simple die set. So now let us talk about the shearing action in die cutting operations. So let us continue with the discussion. Let us talk about the shearing action in die cutting operations. The cutting action that occurs in blanking and piercing is similar to that of chip formation ahead of the cutting tool. So the cutting action proceeds in the following stages. So we call this as shearing action. The reason is we have a press, we will punch, which moves down over the die support. See, this is the sheet metal. So there is a sort of sliding action at the place where the shearing takes place. So the actually it proceeds in stages. If you look to the stages, what are the different stages? So the first stage we call it as elastic plastic rollover. Elastic plastic rollover. So in this stage 1, we find that a sort of radius is formed around the punch corner as well as die corner in the sheet metal. So this radius is called as rollover radius. So this radius will be larger when the clearance is larger. Similarly, the material is more plastic or more soft, then we find this rollover radius to be a larger value. Second stage, which we call it as burnishing. In this burnishing stage, there is going to be a sort of penetration of the punch into the die block, into the sheet metal. Similarly, there is a rubbing of the sheet metal by the die walls, or rather the work material penetrates or moves into some more moves closely into the die opening. So that is known as burnishing. So this burnishing will be observed as a bright polished band uh, inside the hole of the stock material that is produced, as well as the outside of the slug. Next, crack formation and fracture. As the punch proceeds further down, we find that the cracks will be produced on the corners. Actually, the around the punch corners in the sheet metal, there is going to be a sort of crack formation. So we find that the cracks will be far in the initial condition as the punch moves nearer and punch and as the punch moves down further and further, we find that the cracks proceed towards one another when the uh, clearances and other conditions are favorable. So under the favorable conditions, we find that this two cracks approach one another very fast and separation of the material takes place. Slug drops into the die opening while stock material, it is ready to be disposed. So this is a characteristic appearance of the edges of the parts produced by piercing operation and blanking operation. So the punch, as it proceeds down, it produces a surface something like this. Just a second. Right. This is how the appearance will be. So one may observe three important regions which are characteristic of the three stages in cutting. Okay. So first we may observe a rollover radius both on the hole that is produced as well as the slug that is produced, right? So this we call it as rollover depth. Then we find a burnished region. So this is this polished region. So this darkened region. So that is nothing but the burnished band. So that we call it as burnished depth. Next we find irregular surfaces. These are all irregular surfaces that are occurring just because of a break that has been created, right? So the ends of the break, we find projections that are nothing but the tensile bars. Tensile bars formed on the hole as well as the slug, right? Next, let us talk about the die punch clearance. All of us accept that the size of the punch is always kept smaller than the size of the die opening. This intentional difference, we call it as clearance. So clearance is necessary to allow the cracks to extend and meet one another so that the break is neat or clean. If the clearance is excessive, what happens? Simple, excessive rollover shall be observed. So when clearance is excessive, the rollover observed shall be excessive. Further edges of the material will be pulled or teared. That means we are going to find large bursts. We are going to find large bursts. On the other hand, when clearance is insufficient, what happens? So when clearance is insufficient, we find that the fractures extended will not meet one another. So there is less possibility of these cracks that will not meet one another in a proper manner. So I mean, the crack that has been formed around the punch corner in the stock material, crack that is formed around the die corner in the stock material, they do not proceed towards one another. They may get offset and they proceed individually. Then a secondary break, we call it as a secondary break. The secondary break is necessary to connect these two cracks. So that is called as secondary shear. So this is not at all expected. So we find a second burnished ring as well as a sort of interference of the material. So this insufficient clearance increases pressure. This increases pressure on the punch and die edges, greatly reducing their life. So this is not at all expected, right? So insufficient clearance, and this is excessive clearance, right? So we find that this is a primary crack, primary crack. This is another primary crack. So they are not moving one another towards one another. So they are offset. So you have a secondary crack or secondary break. Which needs to connect them because they are proceeding individually. They are not expected to meet in normal manner, right? When we talk about the amount of clearance, we provide clearance as percentage of stock thickness. Generally, 5 to 10% of stock thickness per side is enough. Next, how to apply the die punch clearances? See, the die punch clearances are applied depending upon the name of the operation or depending upon the type of operation. When we talk about the blanking operation, we apply clearance to the die because the size of the opening, the size of the die opening will correspond to the size of the blank, and therefore we apply clearance to the punch. That means the punch is made smaller. So in the case of blanking, punch smaller than blank size. On the other hand, when we talk about the uh, piercing operation, so the piercing hole is decided by the size of the punch. Therefore, die opening has to be excessive. So die opening excessive, die opening excessive compared with punch size. Or simply we may write with respect to blank size. So die opening excessive compared with blank size, right? So this is how we apply the clearance. So there is another clearance which we call it as angular clearance. What is this angular clearance? So you may observe that the uh, okay, we may observe that the die uh, walls are not straight. So part of the die wall is straight, and from there it will be tapered down. So this tapering is done because whenever the punch pushes, whenever the punch pushes the stock material into the die opening, there is a sort of elastic deformation. Once the punch releases from the cutting action, there is going to be a sort of elastic recovery. And therefore, we find that the blank increases in size. So we find that the slug or the blank expands. This expansion in blank dimensions will make this blank to stick or cling against the walls of the die opening if it is straight. If you provide a tapper, simply the blank, on account of the elastic recovery, will not be able to still hold against the walls because it's tapper and simply they will drop down. So this will often also prevent stacking of the blanks. That means blanks placed one over the other, and increase in the punch force. All such type of problems are eliminated. Okay. So the next discussion is about press tonnage. So when I talk about press tonnage, we use the word tonnage because the amount of force which we require, is in tons. That means large amount of force is required. Force required to penetrate the stock material. We, if we try to calculate what is the numerical value of that force, we write it as SPT. S stands for the ultimate tensile shear strength of the material. P stands for the perimeter and T is the thickness of the stock material. So this much amount of force is required, right? So one should definitely remember that S stands for the ultimate shear strength. It is not ultimate tensile strength. It is ultimate shear strength of material. Okay. When we talk about the uh, um, force after it has been calculated, we should be aware where we have to apply this force. The place where we have to apply this force, it is called as center of pressure. This center of pressure, uh, it is nothing but the center of gravity of the line that is perimeter of the blank. It is not the center of gravity of the area. Once the center is found, the press tool is so designed that center of pressure will be exactly on the axis of the press ram along which the cutting force acts. So if we don't apply the force along this center of pressure point, there is going to be imbalance of forces. So we may find a sort of bending moment, undesirable deflections, and misalignment. So these are all different type of troubles which we are likely to face. When it comes to calculation of center of pressure, so these are the different steps. First, draw the outline of the portion to be cut. Draw the x-axis and y-y axis at right angles at a convenient position. When there is symmetry, we can make the x-axis or y-axis pass through this axis of symmetry or line of symmetry. Next, divide the cutting edges to be cut into simple line elements. Please understand these are line elements. These are not area elements. These are line elements. Next, find length of each of these lines. Next, find center of gravity of each of these lines. Do not confuse with the center of gravity of area and center of gravity of um, do not confuse this with center of gravity of area. Next, find center of gravity of the first element from the y-y axis, which we call it as x. Similarly, say for the first element we call it as x1, for the second element we call it as x2, and so on. When we apply the formula, this is the formula for center of pressure. Xy is equal to L1 x1, L2 x2, L3 x3, etc. divided by L1 plus L2 plus L3. Next, L1 y1 plus L2 y2 plus L3 y3, etc. by L1 plus L2 plus L3 and so on. Right? So we may look to this example how we have calculated the center of pressure. Next, when we talk about the methods of reducing punch forces, the methods of reducing the punch forces are multiple. The first method, it is providing draft on the punch or dies. This is how they look like. So instead of the punch looking straight, that means its face is not perpendicular to the axis. Instead, it is inclined. So by doing like that, we are able to reduce the load on the punch. Actually, the peak load is reduced. The load is not, the force is not totally reduced. The peak force is reduced because the cutting will take place gradually. It will not take place on the complete contour. Instead, it cuts gradually along the contour, right? And when we talk about the amount of draft, we can provide different amount of draft, say something t by 2, t by 3, or even sometimes of number of one time of thickness. So in each of these cases, we find that the peak load will be reduced and therefore the punch will have more life. Similarly, die and other components will have more life, but there is likely distortion of the workpieces, right? So we may find that the die opening or punch face may have a draft as a single draft or a double draft, similarly convex or concave shapes. Another way of reducing the punch forces is staggering of punches or stepping of punches. So punch 1, punch 2, punch 3, they may be staggered. That means once the punch 1 completes the cutting, then only the punch 2 enters, then only the punch 3 enters. It will go on in this manner. So this is the case when we have operations which require progressive dissects, right? Further, it has to be remarked, or rather kept in mind, that the slender punches or thin punches, they have to be supported properly. So use pedestal punches, use a quill, that means a sort of supporting cylinder. Likewise, use a backup plate, combine the punches or grouping the punches. So this is a case where this is a case of staggering and mounting both. This is a case of grouping the punches, right? So wherever it is possible, we can group these slender punches. So this will provide more support for the slender punches. Right. So the next point of discussion is progressive and compound dies. What are these progressive dies and compound dies? So when I mean by progressive, it is gradual or step by step. So we produce the component step by step. Say we require a washer, something like as shown in this diagram. We first need to produce a hole, and then we need to produce a separation from the stock material. That means outer contour is punched. So for this, what we can do is we can have in one station the piercing punch and piercing die. In the second station, we have a blanking punch and blanking die. So once the sheet metal passes through station 1, the component hole is punched. That means inner dimension is produced. Next, I will push this stock material forward by a distance which we call it as advance. So now the blanking punch lowers down, producing the outer contour of the component, right? So this is another example where we can find number of operations are performed, multiple of operations. Say station 1, station 2, 3, 4. Station 1, square hole produced. This 3 edges are cut. Next, that means this is sort of trimming operation. Next, edges to this side are produced. Next, 4 holes are cut, and the last station. So this last station we are going to do a parting of, right? So all these things produce components at a faster rate and in a controlled manner, right? This is called as progressive die. So for this, some of the or rather more number of accessories are required. So what are these accessories required? Extra fittings required: stripper plate, pilots, stops, of course, starting stop or an automatic stop, sometimes punch center knockout. These two are particularly needed. So these are more needed in case of compound dies. We'll see how it works, and there we'll discuss about this. So this type of die set, we call it as progressive die set. So let us look to the compound die set also. Then we can go back to the scrap set layout. So this is a compound die set where we perform the punching and blanking. So it is, we can better understand in this diagram. So punching, piercing and blanking. That means inner contour of the workpiece and outer contour of the workpiece. They are produced in one station. So compound die, it is nothing but a single station die. So single station die where two operations are performed at a time at same place, right? So if you look to the construction, we find that the center one, it is nothing perforating punch which will produce a hole, and it has some additional arrangement. So you can look, this is the blanking punch and perforating die. Ante it acts as, the outer surface acts as punch for producing blank, while the inner surface helps in producing the uh, insert connections faster. So continuing the discussion about the compound die, I may repeat repeat that these are single station dies where two or more operations are performed at a time and at the same place. So we may uh, notice that the blanking punch outer surface acts as blanking punch, but inner surface acts as a piercing die. So this is this portion. It may act as piercing die. Likewise, so this part, it may act as uh, piercing blanking die. Okay, sorry. You may find that this, the upper portion is the blanking die, right? And the inside portion, and the inside, so this is the blanking die, and this one, it acts as the outer surface, acts as the blanking punch, right? So blanking punch. So this is nothing but the blanking punch. So inner surface acts as the piercing die. The outer surface acts as the blanking punch. So that is a schematic diagram. You may not find all the information. So this is a better diagram. Blanking punch and piercing die. So blanking die. So in addition to this regular die and punch setups, we have knockout rods and knockout collar. See, the blank has to be pushed out by some additional means. So you find that knockout rods ఇక్కడైతే పూర్తిగా చూపించట్లేదు, పార్షియల్ నాకౌట్ అన్నారు ఇక్కడ. కరెక్ట్గా చెప్పాలంటే ఇక్కడ నుంచి బ్లాక్ నాకౌట్ రాడ్స్ రెండు రావాల్సి ఉంటుంది, రైట్? నాకౌట్ రాడ్స్ హ్యావ్ టు కమ్ ఇన్ దిస్ మేనర్. సో ఫైనలీ దిస్ నాకౌట్ రాడ్స్ they should join with a collar, which we call it as knockout collar. కొంచెం పైకి ఉంటుంది. So something like this. So this we call it as a knockout rod. And the knockout collar. So one may understand that I have to push this knockout collar down so as to eject the components. So this is done because this knockout collar, the action is called as knocking out. It has to knock out the component that has been produced. The reason is there is no tapered surface. See, for the piercing operation there is a tapered surface in the die, but for the outer portion, that is the blanking portion, we don't find any taper or draft. Therefore we have to additionally knock out the component which is sticking or clinging to the walls of the blanking die, right? So this is of much of not much of industrial importance, and this may be preferred when we have loose blanks, or rather we tell that we have blanks which are small pieces instead of a strip or a sheet. Okay. Further, we have an advantage in this case, that is the dimensional accuracy is very good. You can find here pierced holes can be held to close tolerance with the edges. Since both inner and outer surface are cut at same place, the tolerances that can be obtained are very good. So clock gears with a central hole and such similar applications where for small jobs where the tolerance and accuracy is more important, we can prefer the use of the compound dies. Okay, so this completes the discussion on the knockout dies also. So finally we may discuss about the scrap strip layout. What is the scrap strip layout? See, the scrap strip layout is something which is connected with usage of materials properly in progressive die setups. So in progressive die setups, the component is progressively improve in features as it passes from one station to next station, right? In such a case, the stock strip which we are feeding there should maintain some requirements. What are those requirements? You may look to the title, design of scrap strip layout. So when I mean by strip, it is nothing but stock material. Scrap, we have written here it as scrap because finally what we are going to get is nothing but scrap. So that scrap has to be minimized. So main considerations in this context of design of the scrap strip layout is choose the best location of blanks to save material. One is saving the material. Another one is choose the best location of blanks to serve good bending when bending is required, or any further operations are required. Still that strip should be useful, right? You can look to examples. So I have arranged this cutting in this manner. You look to the second case. Here the scrap which we are getting is relatively less. You look to the third case. where I have changed the design. I am not using any rounding off at the corners. So I am providing a straight corner. So in this case 3, there is going to be enormous saving in the material, and I am going to get a very small amount of scrap, right? How can I make this scrap strip layout? How can I carry out this? So for this, what I have to do is I have to take a cardboard or celluloid template cut in the same manner as the contour of the workpiece. So this template is placed in various positions adjacent to the workpiece outline until the most favorable relationship is obtained. That means the template will put it in different alternate ways so that we are able to generate the alternative ways of layout, right? Sometimes it is directly possible to understand which is better one, but sometimes we find it will be more complicated, or will not be able to appreciate which is useful. So for that we can go for mathematical calculations. So for a particular type of layout, we can calculate the percentage scrap or percentage utilization. So A minus B by A into 100, B minus simply B by A into 100. B corresponds to area of the strip which we obtain. A corresponds to the area per blank that has been utilized for this particular job, right? So by doing like this, we will be able to estimate the material savings, right? When we are having irregularly shaped jobs, the area calculation will become more complicated. In such cases, we have to go to a formula. Total area used per blank is equal to random length of the strip into width of the strip divided by number of blanks obtained in that random length of the strip. So we take up what is going to be the random length of the strip into width of the strip, right? So total number of blanks obtained in the random number length of strip. So the layout with the lowest area per blank, obviously the area with lowest area per blank will become the best selection, right? Um, when we talk about the scrap strip layout, we can't tell that the best strip layout is the one which utilizes the material in the best manner. It's not like that always. We have to look to the design of the die. For example, for the best utilization, you may require a complex die. Complex die means, so the initial investment is going to become large. So we cannot go for such investment unless the number of components required are relatively large, right? Further, when we make a design, we should be careful that the blanks are not located too close to one another. So blanks located too close to one another or edge of the strip, what they do, they don't allow the cutting. Instead, they simply allow the metals to slip. So the metal will simply slip into the die opening. Huh? And further, the scrap skeleton must be strong enough to withstand the feeding forces in a progressive die. So feeding forces could తట్టుకోవాలి. As a generally, what we do is web thickness should be at least 1.5 times of stock thickness. Huh? So this is a thumb rule, and there are many other factors which will decide this web thickness as well as distance from the edge, such as hardness of the material, thickness of the strip, type of operation, whether it is a 2-pass die or single pass die, and so on, right? So here you can find some optimization calculated and carried out so that you will be getting a better strip layout. So this one says you waste so much of material, but here the width of the strip, width, say here it is W1, here the width is W2. We find that just by changing the orientation, we find that W2 is less than W1. Second case, see, instead of a single die, we are having two dies. So we are cutting along two rows. So we may use a gang die, or we may have to use a 2-pass die. Just by increasing the width by a small amount, I am able to make more number of holes with a slight increase in the width of the strip. So in this case, we require gang die. or we have to go for 2 pass die. We have to go for 2 pass die. That means feeding left to right and feeding right to left. So likewise, you can look. This is also another case. Huh? So in this case, increase the width, but not much use compared with the third one. So these are all examples of optimizing. Okay. So this completes the discussion on scrap strip layout, and of course the networking is almost complete. Thank you.